Perales from the University of Mexico, Oaxaca, who is going to talk about intrinsic flat stability of the positive mass theorem for graphical manifolds. Please, Raquel.
Okay, but we are going to be dealing with dimensions bigger than or equal to 3, okay? So it says that if you have a Riemannian manifold which is complete and asymptotically flat, and the mass, the ADM mass equals 0, then your manifold has to be the Euclidean space. And the aim of this talk, as the title suggested, is a stability result of this rigidity result. So what we are going to do is make the mass, well, we will have a sequence of manifolds, and the mass of these manifolds is going to converge to 0. And we want to say that in the limit, these manifolds converge to Euclidean space. And the distance that we are going to be using is intrinsic flat distance. And the point of this distance is, as you can see in this picture, here in this picture, so we have spheres, 3-dimensional spheres. You can put a non-negative curvature on them. Oh, sorry, I mean these spheres, I have these spheres that have these splines, and then my sequence is to get more and more splines. The splines become thinner and thinner and thinner, and with this intrinsic flat distance, they will converge to this nice round sphere that is inside. Okay, so let's continue, and let's start talking about graphical hypersurfaces of Euclidean space. So this is a definition. It does not appear as a definition in the paper by Huang and Li, but I wrote it this way. And well, as I told you, we are going to be working with manifolds, which are going to be graphical manifolds. So we are going to have a function f that is going to be continuous outside some open set U, and that is going to have that is going to be of class Cn+1. So this is my function. You can then write the graph of this function. You endow it with the induced Riemannian metric, and you require this graph to have non-negative scalar curvature. You require some asymptotic flatness conditions. I wrote them here, but if you know asymptotic flat, just think that is regular asymptotic flat. And one word about this set U. This set U could be empty, so then we don't have boundary, and we say that our graph is entire. Or if this set is non-empty, we require the function to be constant on each component of the boundary of U. And we require this condition on the gradient of the function f when x approaches the boundary of U. So that would give us the minimality of boundary of U. Okay, so let's continue with this definition. And I guess it's this. We require these two more conditions. This condition is telling us that we require the level sets to be strictly mean convex and outward minimizing. And this must hold for almost every level set. And you just should think about the regular values of your function, which is almost every point. Okay, so this should be strictly mean convex and outward minimizing. This is not such a big condition, as I'm going to explain later. And in the case of dimension 3 and 4, we require our function to be close in this sense to the function of the function s. So here, so we want f close to this function s, and s is the function that embeds a Schwarzschild manifold in dimension n+1. Riemannian Schwarzschild in dimension n+1, and we just take one of the n's. Okay. alpha, I mean, it's a part of the definition. Alpha is some constant that you fix and should be less than 0. Okay. So before telling more about the stability result, I want to make some remarks about this definition, about this class of manifolds, and especially the manifolds that only satisfy the conditions in this first slide. So these manifolds were studied before by Lam and by Lan and Gu. So let me move forward. Oh, okay, sorry, I forgot how my slides go, but let's read this theorem. So in this theorem, we already have some stability result. So it's the same class as before, this Fn R0 gamma alpha. We require the ADM mass of some sequence to go to 0, and we get convergence to the Euclidean space. And this is basically the picture. The picture is you renormalize your function, and once that you renormalize your function, this is your manifold. And you want to take flat distance here, and if you know about flat distance, it only requires to put some good orientations and then calculate the volume of B minus, B plus, and A. And why can we ensure that this converges to 0? Well, the trick is the following. In this part above this horizontal line, we will have that this height is controlled by the mass. So here we have a term of the mass. This term, sorry, also works for manifolds of dimension n greater or equal than 5. If you have dimension 3 and 4, there is a different scaling, but it's very similar, the picture. So then this height is very small, so then you can calculate the volume of this part, and it's going to go to 0 if the mass goes to 0. And in this part, what we are going to have, even though the picture doesn't show it, the level sets in the part below are going to have a small volume, and then you can use isoperimetric inequality. And this small volume is also controlled by the mass. So then this part is also, its volume, it's also going to go to 0. Now for this boundary part, what we are going to have is to use Riemannian-Penrose inequality. So because of the mass goes to 0, then the volume of these A's are also going to go to 0. Okay, and so we have this result. Okay, let me now continue. And as I told you, these slides are just to convince you why the graphical case was so good. And I mean, there is a formula for the scalar curvature for the mass, and there is this nice relationship between the mass, and here the scalar curvature appears. And here we have a very nice quantity that actually is positive because this part, this h, the mean curvature of sigma h, is going to be positive. Okay, and let me continue. This is just to show you how nice graphical case is. Okay, and as I was telling you, this h sigma is going to have positive sign once that we replace f by its negative, because the graph is always weakly mean convex. So we can really choose the picture to look as I was telling you. So the graph, you flip f and then it looks like this. And what Lan and Gu proved was that then you will have this h to be greater or equal than 0. Okay, so let's move on, because what I want to do is, okay, this is just the explanation of the existence of this nice height for which level sets below are going to have small volume. And here, look at the small volume. This is our quantity. So level sets here have a small volume. And in this part B is non-decreasing, is telling me that this volume function, so BH, which is the volume of the level sets, it's non-decreasing. And that's why this value H0 is really well defined. And then the next line, is telling me that one has a differential inequality that in terms of this B function, and this functional inequality will give us the part that I told you before, that in the upper part, this height will be controlled by the mass. Okay, so that's the picture of this class of manifolds. And now let's move on. So once that Huang and Li proved this stability, flatness, with respect to the flat distance, Huang, Li, and Sormani tried to prove stability using intrinsic flat convergence. And for that case, I mean, flat distance or flat convergence does not imply intrinsic flat convergence. That's why it's nice to study this problem. And also, intrinsic flat distance is an intrinsic distance, as the name says. So one has to impose more conditions on the class that Lan and Dan already had studied. So the conditions that we impose are these three extra conditions. So the first condition is that the set U that we removed from Euclidean space, so the part that corresponds here below, or let's say this part, I don't know, that should be contained in this ball of the fixed radius R0 divided by 2. The second condition is that the norm of our function has to be bounded outside of the region, outside of this ball of this fixed radius R0 divided over 2, so that this part will give us control of the outside of the manifold. And in this part, the third condition, we put some control on the inside of the manifold. So the control is telling me that if I start in this level set sigma R0, that corresponds, okay, if I have this, if I look at this level set, and I look at the distance from this level set to all the points inside, then this distance is less or equal than this constant d. Okay, and this is the class in which one is going to prove intrinsic flat convergence. Are there any questions? Okay, if not, this is the theorem. So the first theorem is like this. Well, maybe I didn't mention, but what we are doing is we have these graphical manifolds, and what we are going to do first is to intersect each graphical manifold with a cylinder. So this is the cylinder, here is represented the cylinder. So we are basically studying convergence of these regions that we call them omega. Okay, and so our result says that these omega regions converge in intrinsic flat sense to the ball in Euclidean space, provided their masses are converging to 0. There are more intrinsic flat stability results. Of course, there are more results that don't use intrinsic flat distance, but I skip that literature. I'm sorry. You can talk to me later if you want after this talk. And the second result is the pointed version of the other result. So now we make actually the balls converge to the ball in Euclidean space. And here one has to be very careful with the points that one chooses to make a pointed convergence. And what one has to do is choose the points in this region sigma j R0. In this region, we know that the norm of the gradient of the function is bounded by gamma. And that's why the points are not going to disappear. If we get to choose points here, then the sequence might disappear in the limit. Okay, and that's why we chose those points. And then, okay, then you might wonder, what is intrinsic flat distance? I haven't defined it. And I mean, if I want to keep it as a black box, then we just should read this slide. And with this slide, it's enough to keep it as a black box. So first, let me comment that there is actually a compactness or well, actually this should be pre-compactness theorem. So there is a pre-compactness theorem, and it is pre-compact because given a sequence of manifolds that satisfy uniform diameter bounds, uniform volume bounds, and uniform area bounds, you can extract a subsequence and say that that subsequence converges. And this subsequence, okay, and this limit is no longer going to be a manifold, possibly, and that's why this should be thought of as pre-compactness theorem. So this is an integral current space.
Can the volume actually go to zero here in the case of the manifolds? And in this case, the limit, I mean, the zero is a space?
Yes, yes, so yes. Zero integral current space exists. Okay. Yes, yes, okay. Yes. Okay. And then, okay. So this is the classical pre-compactness theorem. But what we are going to be using is this theorem, in which you don't need to know what is an integral current space. So we have a sequence of Riemannian manifolds. Actually, we are going to have, is this working? Okay, I think it doesn't work anymore. But we have a fixed manifold, M. And in this fixed manifold, we want to know what's, actually, we have a candidate for the limit. So this limit, M0, is going to have a Riemannian metric, G0, and this G0 make it smooth. And assume that your manifold with this Riemannian metric G0 is totally convex. And then, in order to have a sequence of manifolds, you just change the Riemannian tensor. So you have tensors Gj. And you require G0 less or equal than Gj, the diameter bound, the volume, actually volume convergence, and volume bound of the areas. And of course, by the line below, you already should have a limit. But this theorem is telling you that the limit should be M0. Okay, so this is the niceness about this theorem. Put this volume convergence, put these tensors with this inequality, and you know what's the limit. Questions up to here?
How much smoothness is required for the matrix here?
Gj only continues.
And G0?
G0, I mean, G0 should be C2 or something, or C1 probably. Yeah, but we just wrote smooth. Okay, so let me continue. If nobody has questions about intrinsic flat convergence, I'm going to skip this part. This is my black box. My black box. The whole sequence. The whole sequence converges. Okay, so we have a black box. Is everybody okay with our black box? Okay, if that is. Okay, so now let me tell you how then one proves such a theorem. I told you we are going to use this result by myself and Brian Allen. And how does the proof go? Well, the proof is, of course, we want to use that theorem to calculate volume, diameter, and area estimates. And this was done in Huang Li and Sormani's paper. So we are going to follow this approach. And then, if the manifolds are entire, so let's say the picture looks like this, Then, of course, our regions, omega j r, which are the manifold intersected with this cylinder. Oh, no, times. Of course, then this manifold is going to be diffeomorphic to a ball in Euclidean space. Okay? So we can use Allen-Perales convergence result. What happens if the manifold is not entire? Then we no longer have this diffeomorphism. So what we are going to do is cap the manifolds off. So again, what do? We put a long cylinder, cap them off, and we want.
What do you mean by entire? Complete?
Entire with no boundary. Yes, with no boundary. Complete with no boundary. Okay. So if these manifolds had boundary, we complete them with a cylinder, then cap them off. This new manifold, let's call it, or this new region, we make these new regions to converge to a ball in Euclidean space. But then what's the relationship with this new region and the previous one, right? So we have to do the capping really carefully. So this sequence embeds into this sequence. And then what we have to know is that this region, this region that we attach, we started from here. The volume of these regions is going to converge to 0. Why? Again, Riemannian-Penrose inequality tell us that the boundaries of U have small volume, so then the cylinder has a small volume, and we make this in such a way that the volumes of this part also converge to 0. Okay. So.
Excuse me. Do you need to assume that pink thing is a minimal surface?
We are assuming that is minimal, yes.
You need to assume that.
Yes. Okay. Okay. I mean, maybe my sketch was said a lot of things, but these are the real computations, how you calculate the diameter bound, which comes very easy because you know what's the metric. The metric is just a graphical metric, Euclidean plus the factor that comes from the functions f. So you have G0 plus dfg tensor dfj. Of course, G0 is less or equal than Gj. And then you calculate the diameter bounds. And the diameter bounds, you just have to remember that there is an exterior part in which we know how the gradient of f, or the norm of the gradient of f, is controlled. It's controlled by this gamma that appears here. And inside the part that we don't know, this part, we impose the condition of this d, that we have this d here. Okay? So, and then just triangle inequality. For the volume of the areas, you get, for the areas of the boundaries, we have two components. The component that we created when we intersected with a cylinder. So the exterior boundary is controlled by this quantity, its volume, and then the interior boundary is controlled once again by the mass, by the Penrose Riemannian inequality. Okay, so that gives us the bounds that we want. And for the volume convergence, we have to remember what I told you, that the picture looks like here the height is bounded, and here the volume of the level sets is small with respect to the mass. Okay, and once that you have that, again you use how your Riemannian tensor looks like. So this is just coarea formula, isoperimetric inequality, and those two conditions that I told you. And as expected, volume below this line is going to be very small here, and it's going to converge to 0 if the mass converges to 0. Volume in the part above, well, it's very close to the volume of the ball, plus some other term that also converges to 0. Okay? So that's how one calculates this volume, diameter, and area bounds. And this was the part that I was telling you about the capping off. Okay. So that was the capping off. I lied a little bit to you. We have to use another version of Allen Perales, but it's basically similar to what I was telling you. Here we have this condition of the Riemannian tensors. So we have again G0 less than this part, which is pullback of the Riemannian tensor. And phi is a C1 diffie-over-phi. Okay. Good. And this proves the first theorem. So the convergence of the regions that we get when we intersect with cylinders. My second theorem, pointed convergence theorem. So what we know is that these regions are converging. And we want balls to converge. And I told you we are going to select points in some level set sigma R0. So suppose this is sigma R0. Here I pick a point P, and I would like to choose or to have a ball converging. Okay. So what we have to do is basically choose a big R, so it contains all this part, and then I can make these balls inside this region. Okay, so that's what I'm doing. I'm choosing a big radius, R0 plus R bar. Then I know this converges to 0, so these regions converge to 0. And then, as I told you, we have this problem with the points. The points might disappear. So how do we deal with that? Well, luckily, we had conditions on the gradient of the norm of the function f. And so these conditions ensure that we have Gromov-Hausdorff convergence in the exterior region. So actually, we just chose an annulus, and this annulus is going to converge to an annulus in Euclidean space with some distance. It's not the Euclidean distance, but it does not matter. And so we can choose a subsequence that converges to some point in this annulus, of course. Okay. Okay. So now we have intrinsic flux convergence in one side, Gromov-Hausdorff convergence in one side of different sequences. So how do we reconcile this convergence? And with Dan and Lan, we prove such a theorem in which it says if you have a big sequence that is converging in intrinsic flat, and if you restrict this sequence to a smaller set, and this sequence also converges in intrinsic flat, this Gromov-Hausdorff convergence implies intrinsic flat, by the way. So then, if you had a sequence that converged in this smaller sequence or sequence of smaller sets, even if it converges in another space, it will converge. So this subsequence will converge for this bigger sequence to a point that might not be the same point. Why we have all these type of things? Because for Gromov-Hausdorff distance, I mean, a priori, you cannot tell if this is realized in a different space set. Okay, and that's why this is difficult. Okay, so now we have the point in the limit to the one we want convergence of this. So this should be our center in this limit space. Okay, so we have here this one. And what we are going to do is now take these big regions that we know that converge, and then intersect them with the small balls. And this is going to converge in intrinsic flat sense to 0, because we already had convergence of the big regions. Okay, and now we want to make sure that this intersection is actually Euclidean ball, because it could be that we have this type of picture. So here we have omega infinity, or let me write it, B with this big R, so R0 plus R bar. Here could be P infinity, and this could be the restriction. So I'm intersecting this limit ball with this ball, but if this P infinity happens to move while it converges, then it only converges to this part. Okay, so we have to be careful about this. So check restrictions equals the balls that we really want, so Euclidean balls in this case.
Excuse me, what is that concept?
Restriction. Yeah, so this comes from integral current spaces. You have a current and you restrict it to one set. And so it's a restriction. But just think of intersection.
It's not symmetric.
Not symmetric? In which sense?
To restrict some current to some subset.
Yes. Okay, and then okay, so this and then the final step in this convergence is that up to here we got a convergence for this sequence of balls. Okay, and this is a subsequence, and in my theorem I stated that the whole sequence converged. Okay, so let me, oh sorry. So this was the statement that the whole sequence of balls converges to a ball. So then one has to do extra work to recover the convergence for the whole sequence. Okay, and I guess my talk is almost over. This is just an announcement. I have upcoming work that is very similar with Armando Cabrera Pacheco and Melanie Graf for asymptotically hyperbolic graphical manifolds. And thank you for your attention.